Hello, everybody. Thank you for joining our webinar today. So today's webinar is called The Rule the Cool Reduction of Energy and Chemical Costs Through Deep Lake Cooling. Our presenters today are Grant Thornley and Pablo Rodriguez. So on the agenda today, Grant will go into the intro to Uponor Infra. We'll talk about what's in the Great Lakes, how do zebra and quagga mussels impact the Great Lakes, how to control zebra mussels, and finally we'll give you the solution, the deep lake water intake lines, and then Pablo will go through some installation methods and some existing projects. So without further ado, I'm going to pass it off to our Director of Sales in North America, Mr. Grant Thornley.
Great. Well, thank you very much, Faze. I appreciate it, and thank you very much, everyone that's online, for taking the time out of your day to join us on this WebEx. I hope it will be informative. Will be a couple of takeaway points for yourself. Before we get into it, just quickly, just to let you know, well, who is Uponor? If you're not familiar with us, Uponor at a glance, we are an HDPE company. We do polymer science and focus on building and infrastructure. From water conveyance to pump stations to radiant floor cooling and other offerings. On a global basis, we're about a $1.1 billion company. We're located in about over 30 countries, as well as North America, of course. Our sites, we have about 14 sites manufacturing worldwide and about 4,000 employees worldwide. Quickly, with what Uponor Infra does, we manufacture 3 different types of products. Again, focused on polymer science, or HDPE, high-density polyethylene. One is our trade name, or very common pipe, is our solid wall, or Sclairpipe, from low pressure to high pressure. Structural HDPE Weholite pipe, which is for low pressure, high conveyance or volumes. Docks, pressure, so on, and then lastly, panels, which we can fabricate into various design structures. Combination of the 3, solid wall, Weholite, and panels, allow us to produce, designed, customized solutions, infinite size, scales, and so just a quick overview. Conveyance systems, this is our Weholite pipe, pump stations and manholes, retention, detention systems for stormwater. Essentially, Uponor makes the largest HDPE pipe in North America. So, getting into the body of the presentation, cooling water from the Great Lakes. There is that we have many manufacturers located around the Great Lakes and the 5 Great Lakes, which are natural water, or fresh lake waters. Them are food manufacturers, power generation, pulp and mining, petrochemical, food processing, and others. I'm sure you've seen lakes. Why they locate there and build their facilities shores is that because it's easy access to large volumes of water, their processes. And the benefit of doing that is that the majority of manufacturing processes require large amounts of volume of cooling water within their processes. And by locating there, that cooling water is relatively free, and I say relative. Other companies that are inland would have to pay surcharges for potable water and so on. So locating on the Great Lakes is a great idea in which to reduce your operational costs and in turn reduce your product costs, more competitive market space. Some examples of the cooling water uses are cooling water makeup and cooling water towers, as I'm sure off of these power plants, or in the winter time, off the top of the buildings. Heat rejection within heat exchangers, they plate and frame, bundle, and so on. Another aspect is some companies actually just run once through cooling, so no loops, just once in one. So some of the aspects and different processes used. Like anything because these bodies of waters are governed by the state and federal, withdraw and discharge into the lakes are regulated by local and agencies. What's in the Great Lakes water? So as you're aware that, I'm going to say from your grade 10 geography classes, that you know that the Great Lakes are located top of the Canadian Shield and also the sedimentary basin, or a very large limestone basin. Because the waters are located on top of these, and the waters absorb the minerals and content from those, we find that the Lake Ontario water is high in calcium, iron, magnesium, and other minerals, depending on what lake you're in. But essentially, they all contain those, just at different concentration levels. The other aspects, other than minerals, you have natural organics. As it's an open body water, you have trees, leaves, plants, other vegetation that will fall into the water and decay, and therefore contribute to the organic levels, which typically refer to BODs, or biological oxygen demand. In addition to that, you have, unfortunately, stormwater or other runoffs going into the Great Lakes, man-made substances, fertilizers, herbicides, pesticides that can also be found in water as well. Fertilizers more so than the others, also because of the farmland as well, with phosphates. So essentially, when you take a look at the Great Lake waters, mineral content, you have BODs and other contaminants. Well, not necessarily you want to have those in your water. So therefore, you're going to mechanical and physical cleaning up of that water. Typically, what you find on plants located on the shores of the Great Lakes is a lot of them have depth or sand filters because they're very inexpensive but very good means of mechanical separation, organics and other soluble substances. And for the insoluble substances, you'll find ion exchange, resins, calcium, magnesium, hardness, as well as sometimes maybe chemical precipitation. So essentially, even though, as I said in the initial slide, I said the water is relatively free, it does come with some costs. You do have to clean it up a bit in order for it to be usable within the processes. So one of the things that talked about is the minerals, organics, and so on. But the other things that you find within Lake Ontario water is zebra mussels and quagga mussels. I had the opportunity to step in some of the lakes sometimes. I'm going to say 10 years back when they first appeared. Zebra mussels are very sharp. They're razor blades, so some cut their feet just going into the water. But just to give you a little bit of history, the first registered presence of zebra mussels in the Great Lakes, they always weren't here, but it was back in 1988 in Lake St. Clair, which connects Huron and Lake Erie. That was the first initial presence or observance of zebra mussels. But within that 2-year time, the zebra mussels, because it's an invasive species and really there is nothing to prevent their proliferation, by 1990, that's 2 years, the zebra mussels had completely infested all of the Great Lakes. So very, very rapid. And you'll see there's a picture of a map representation in red that represents all the infestation of zebra mussels and quagga mussels, with a very high concentration, of course, by the Great Lakes. Where it came from, zebra mussels and quagga mussels actually entered the Great Lakes through great tankers through ballast water. So the transatlantic ships coming from Eurasia would dump their ballast water in the Great Lakes, and of course, when they dumped the ballast water, anything in those ballast waters would be dumped out and would contaminate the Great Lakes. So not only zebra mussels, but there's other fish and other other invasive species. But for this presentation, zebra mussels and quagga mussels. So it it was at this point, once you've contaminated the lakes, it's too late. You can't prevent or remove the zebra mussels. There's nothing really to remove them. So what you're looking at is really how to prevent the growth and proliferation from them to levels that are destructive to infrastructure and also clean water processes. Although these mussels, in some ways, just so you know, that the zebra mussels have, because they filter the water very large volume through their or gills, they've really done a great job in cleaning up the Great Lakes. Of course, that does come with other side effects, but they've cleaned up the Great Lakes. But the other aspect of proliferation is that there are just so many of them. And as an example is that the females lay up to about 100,000 eggs during their reproductive. That's just one zebra mussel. See in the top right-hand corner, that's a picture of a zebra mussel on the left and the Quagga mussel, which is a little bit larger on the right. But for relative scale, it's about the size of your baby fingernail. So zebra mussel and Quagga mussels, the reproduction, as I said, there's about 100,000 of them per zebra mussel. But one aspect to it is that the spawning temperature of these mussels require a minimum temperature of about 54-12 degrees C to reproduce. The lifespan of these zebra mussels is 4 to 5 years. Quagga mussels, they require a lower temperature at around 41 degrees or 5 degrees. On the right-hand side here is a scale, more or less the, I'm going to say the surface water temperature, maybe about 10 feet below the surface of the water, 10 or 20, I should say. And you see the line here, it's 15 degrees. See that once June comes around, the surface temperatures rise and they don't drop below 15 in November. So during that period from May to November, that's when the zebra mussels are. Quagga mussels, as indicated, are better adapted to colder environments. Both zebra mussels and Quagga mussels are depth that temperature. Also, just for reference to let you know what the depth of all these lakes are, is Lake Superior is 1,333 feet all the way to Lake Erie, which is the shallowest that we run. But all of them. So reproduction of the zebra mussels occur above, relatively speaking, at 15, which is very, very common. So when they're reproducing, zebra mussels just they're not formed as hard mollusks, but they go through a phase of a larvae phase, and then when the larvae phase, then they attach themselves to hardened surfaces. So Quagga mussels attach most substrates. They typically like hard substrates, but they're also able to attach to sand, silt, and softer substrates. Usually they prefer harder substrates or rocky substrates, such as pipe surface. When the eggs hatch, as I indicated, the zebra mussel larvae emerge, and this is as veligers. The veligers, which are the non-shell hardened mollusks, the veligers are free swimming. They can drift in the waters for several weeks looking for substrates or surfaces to attach to. So they can exist for a very long time. One thing to understand with the veligers, the veliger has, you can see in the top right-hand corner, these bundles or the bias fibers coming out of the mollusk, and that's sometimes commonly referred to as the foot. So when they're drifting around looking, they have this foot sticking out, or a foot or a hand, whatever you like to refer to, out of the body of the inner body of the mollusk, looking, and they're going to use this biases or foot to attach to surfaces. So as more and more mollusks attach themselves as they come into mollusks attached to the inside diameter of pipes, you can imagine that form layer upon layer upon layer, and by doing that, you continue to reduce the diameter of the pipe on a regular reduce. And by reducing the diameter of the pipe, of course, what occurs is that I'm reducing the volume of water that can pass through. Then, as a consequence, in order to maintain that, I may have to increase my pumping pressure or the amount of energy required to maintain the amount of cooling that I require within my processes. So just on the right-hand side, there's I'm going to say, a very common picture, unfortunately, of a pipe that's completely blocked with mollusk or zebra mussels, Quagga mussels. Some additional examples of zebra and Quagga mussels that are very common on the Great Lakes on an annual basis. Is what you find is that companies do a shutdown, a scheduled shutdown to clean off the mollusks from surfaces. Here's a picture on the right-hand side of a penstock, intake of a power plant, blocked trash racks, blocked cooling pipe, blocked heat exchangers, seawater intake for municipal potable water plant, and production in there. See that the other aspect is that not only do you reduce the diameter of your pipe, but also, when we take a look at hydraulic fluids movement, is that the surface smoothness of the surface of a pipe also contributes to the hydraulic flow values to fluids. So the rougher the surface, the harder it is to pump in more higher energy, and the harder it is to pump through that pipe. So not only does it block, but also it increases operational costs because it's harder to pump water through the pipes. So now that we know that we have these zebra mussels and havoc, well, how do you control zebra mussels? Well, there's several means by which to try to control or prevent the infiltration of zebra mussels in a plant's water systems or water lines. Part of that is filtration, which is mechanical filtration. Mechanical filtration, ultraviolet, which is UV, which has some positive aspects to it. But the main one, the most commonly used, is chemicals. And the chemicals when the chemicals are used during the mollusk reproductive periods, and that is temperatures above 15 degrees C, so you don't use chemicals all year, just during those high temp periods. You could use, for the chemicals, you could do a type of mollucides, which again would have to be approved by the EPA. Some of the mollucides act by actually coating the gills of the zebra mussels and suffocating them, and when that happens, they die and then they slough off from the pipes. I've been involved in some of those operations where mollucides were used, and the interesting to see is that sometimes the mollusks or the zebra mussels slough off the pipe at uncontrolled rates, which causes, I'm going to say, havoc within the plant. But because when these break off, they could be like cinder blocks, and when they hit a pump, they could shatter the impellers or even bend shafts of pumps. So mollucides are used, but I'm going to say more so when you have to clean the pipes out. A more common one is sodium hypochlorite, or commonly referred to as chlorine, which is an oxidative chemistry, meaning that it kind of burns the organics up, and are widely accepted by governments in Canada and in the U.S. It creates the octave chemical creates a very, very hostile environment for the veligers, and what occurs is when the veligers sense that very hostile environment, that foot that we talked about, or the byssus that extends from the mollusk, actually it retracts and pulls it in because it's hostile and it does not want to be affected by that, so it goes kind of it retreats. And when it retreats, it no longer has the ability to attach itself to its surfaces. So that's what chlorine does. It causes the retraction of the bicysts, or the foot, so they will not attach themselves within the pipe or hard surfaces, and therefore the veligers actually just pass right through. It comes to the intake, goes through the processes, and it passes through without attachment. In order to do that, the typical chlorine dosage, and we're talking free chlorine, not total, free chlorine dosage rate is between 2 to 4 milligrams per liter, or ppm of free chlorine, and that is injected again during the productive periods. Any chlorine introduced into an intake line has to be removed before that water is discharged back to the receiving body. So therefore, another chemistry is used to neutralize the chlorine. Typically, that is sodium metabisulfite, and its dose is around 1.5 ppm per 1 ppm of free chlorine. Depending on the volumes of water you're using, that is a lot of chemistries, and it could be significant costs in order to maintain your systems, anywhere from $10,000 to $200,000 per year. And that does not include, when we talk about costs, about the maintenance of the control systems, and also if there's what the fines may be if there's violations and controlling these chemistry systems. The chemistry systems, they work, but they're finicky, and they're also prone to issues. To give you an understanding of the type of chemical control system for the zebra mussels, chlorine is injected, as you can kind of see on the right-hand side. It's injected into the intake water using a dosing system, and that dosing system then has a feedback. So I inject the chlorine. I have an instrument that measures it further downstream, and then it then adjusts it accordingly to make sure I hit the set point. Typically, a probe is a typical probe to do that is an ORP, or oxidation reduction probe. They're inexpensive, and they're used very readily within those applications. They are prone to fouling, and they're prone to drifting. So regular maintenance is required, and I'm going to say the increased frequency of maintenance is required, particularly during the higher reproduction periods when the water temperature is above 15 degrees. The chlorine or neutralization is the same methodology. You have an ORP probe that measures the chlorine. It injects the appropriate metabisulfite in order to get the concentration down to 0 before discharge. And it has to be 0, or else it would be a violation. The whole thing, because there's a lot of instrumentation, controls, chemical pumps, there is I'm going to say a large capital and operational costs associated to these systems. It could be high or low, depending on the cost, again, depending on the volumes associated to these processes. And it's not uncommon for the instruments, as I said, to drift out of calibration because of the fouling. So just a quick overview of the zebra mussel control. And again, you're not killing the zebra mussels, you're preventing them, using the chlorine to prevent them from adhering to surfaces. Well, there is a much simpler way in order to address zebra mussels and prevent their infiltration into plants and prevent them from adhering onto lines. And it's quite simply, I'm going to say it's a simple and elegant solution, which has more economics and better environmental, and is more of an environmentally friendly approach, is controlling the temperature of the water. And if I can control the temperature of the water below 15 degrees, or get the water below 15 degrees, then zebra mussels will not proliferate. And so how do I do that? Well, as we saw in a couple of slides back, the Great Lakes are very deep. And if I go down below the surface temperature, the isocline, so the temperature of that water, starts dropping significantly. So much so is that typically at the bottom of the lakes, you're talking about a couple of degrees C. So by taking your intake water line, your pipe, and dropping that to the depths of the Great Lakes, we actually drop below, we encounter temperatures that are significantly below 15 degrees, where zebra mussels, and in some cases quagga mussels, do not exist. In addition, because of the depth, organics are very low, which in organics may foul heat exchangers, so we minimize any organics algae. It would not be present. And what results is that I now have cleaner and colder water coming into my plant, which would allow me to actually reduce my operational costs. As a rule of thumb, 2 to 5% reduction, but we've seen higher reductions as well. Of course, that's a percentage and that we return on investment if you were to install a deep lake intake line would be applicable to what your overall costs, annual operational costs would be. So that is to give you an overview of the issues or the challenges of using Great Lakes water as cooling water, but the solution of getting rid of the zebra mussels and getting rid of the chemical and actually reducing operational costs is really a pipe away. So in saying that, I'd like to turn this presentation over to Pablo, who will take you into a little bit more depth of what's involved in installing a deep lake intake line within freshwater or even oceans or water bodies. With that being said, Pablo, take it away.
Thank you very much, Grant. Thank you for this presentation. My name is Pablo Ramon. I'm from Uponor Infra in Finland. I belong to the Project Services Department, and we are in charge of all the marine projects all around the world. I mean, projects for big or large diameter pipes with Weholite, that is the pipe that we are going to talk today. I would like to show you 4 projects that we have carried out last 3 years that can show a lot about how Weholite is installed in this kind of applications. The first project is a cooling water system for a refinery in the province of Bataan in the Philippines. And we made here an intake and outfall. The intake was a Weholite pipe of an ID of 2,400 millimeters with a total length of 610 meters. And we also made an intake tower made of Weholite Weho panels. We as Project Services Department were in charge of the design and engineering of all the parts involved in the pipeline, including the intake structure. Of course, we delivered the pipes and also the welding service. And not only that, because our department is always in charge of the supervision of all the installation of the pipes or intake heads that we manufacture. In this case, we made 3 railways that we also supplied, 3 railways with rollers. We welded the pipes on those rollers, and once they are ready, we continue with the profile filling method. That is a patented method by Uponor Infra. And with this procedure, what we are eliminating is all the problems that fabricating and handling heavy and difficult to handle concrete colors is on site. So once the pipes are welded, this is the following procedure. As you can see at the bottom on the right side, you can see the automatic machine that we use to weld the profiles, and we weld the pipes with the same material as the pipe is made of. We normally make sections of strings depending on the availability on site, but it's normally from 100 to 250 meter section. You can see that if you look on the left side of the slide, you can see a female flange, and the other on the right side you can see the female flange. These flanges are designed and developed and manufactured by Uponor Infra. And the good advantage of these flanges is that the connection time below the water is totally reduced, because it's saving a long time for alignment and for placing the bolts. the male flange has a loose flange that can rotate, and this, as I said, this saves a long time of diving, and diving is always expensive when we are talking about these projects. You can also see a small pipe, solid wall pipe, that is the chlorination pipe, that normally, of course, it's a pressure pipe, and the concentration on this chlorine, it's around 4 to 5 ppm parts per million. So this guarantees that the intake head will be clean at any moment. I was talking about the profile filling method. As you can see in the picture, this is nothing complicated. We use the standard equipment like a pump truck and a concrete truck. The process is quite fast. The material that we inject inside the profile can be mortar, can be concrete, can be fly ashes. We don't have any preference for any material. Just we adapt it to the materials that the customer has in the surroundings and the materials that are cheaper to be used. The only condition for these materials is that they should have the right specific weight, about 2.1, and that this material can be pumpable inside the profile. As I said, well, we manufacture the intake head for this project with the same connection system with the steel flanges, and the chlorination line was connected to the pipe and going through the wall of the intake head, and this chlorine was spread on the walls of the intake head by some sprinklers. This was one of the models that we can manufacture, but there's no standard model. This is the one that we chose and designed because it was easy to install, it was light, and the total weight, including the concrete slab that you can see at the bottom, was no more than 75 tons. That was quite important, especially for the customer, because they didn't have so heavy equipment as to handle big loads on top of the barge. The cranes they had on the barge were very old, and the limit they had of lifting capacity was 90 tons. So you can imagine how many problems this was solving and how cheaper this was, because this was installed in 2 phases only. First the bottom part and then the top part with the screen. It's this picture is just showing the last section being installed with no concrete colors. It's already ballasted, and by using these airbags or yellow balloons that you see there, we can control the sinking. So at any moment we know what is happening in the pipe, and it's not a problem to deal with the pipes, or if you don't have very heavy equipment, because we are eliminating all the problems that the concrete colors normally cause. For the outfall pipe, we were designing these diffusers that, as you can see, they are very simple, but since this pipe was in a continuous operation, they didn't need to have any duckbill valves or anything similar. So we chose the best and the most economical solution to suit the customer's requirements. The installation onshore of this outfall was a little bit complicated because there were 2 slopes that had to be the pipe should be adapted to it, and it took some time from the customer side, but at the end it was solved with no major problems. And the launching, it's another operation that it's much easier since we don't have the concrete colors. The launching, when you have concrete collars, becomes very complicated. You need heavy cranes, and you always have the risk to damage the pipe because some of the concrete collars could slide. This belongs to the installation of the outfall pipe, and it was a really simple operation. You can see at the bottom on the left that there are some kind of rods on top of the pipe. With these rods, we control at any moment the bending radius that the pipe is adopting in every moment, because this is the most or the riskiest part of the installation, controlling the bending radius and doing having a controlled operation at any moment. This is the same. You can see at the end of in the center of the picture, you can see the cofferland that was built to connect to the onshore part. Another project that was quite demanding from the tidal condition point of view was in Beckton. We made an outfall with Weholite ID 3000, 2 lines of 440 meters. The problem with this is that we had only a few hours to work because the tide was changing from its low level was and between the low level and the high level was 6 meters difference. So that was limiting a lot the working hours. Another problem we found there is that the customer wanted to have a service life of the project of 100 years. This is extremely difficult when you talk about steel. Not even placing huge zinc canots or even with stainless steel, you can guarantee that service life. So the solution we found for that was making these kind of boxes that you see on the left-hand side on the top, these huge boxes, and put the flanges there and pour concrete, cast them into concrete, so we could guarantee the 100 years. There was no problem for this service life from the polyethylene, but the limiting part in this case was the steel flanges. You can see the works in the cofferland during the workable hours that the tidal conditions allowed us to work. And also the huge boxes that we have to pre-assemble in the factory, and that we were transporting them in modules to the installation site since the factory was not so far away from there. So we could do this solution that was making life much easier for everybody. Another project is Nissan in Vietnam. We made an outfall of something around 2 kilometers in ID 2.7, and the diffuser part was 180 meters in 3 different sections of 60 meters each, reducing from 2.7 to 2.4, from 2.4 to 2.1, and from 2.1 to 1.7. The sections in this case were 180 meters, in the same way that we did in the former project in the Philippines. We made strings of 180 meters, and once we had them already prepared, we were launching them one by one. This is the work site. You can see the 3 railways that we prepared and how we planned the work inside with the pipes storage on the right-hand side. This diffuser part that I was talking about, you can see the reductions made of Weholite, because we can do almost everything with Weholite, and the different flange connections for the different diameters. one more picture of the launching days. The crane that you see there is only necessary because when the flange is coming out to the water and the last flange at the rear end of the pipe, it's coming out to the water, we don't get it to get damaged. So we are helping the pipe to be lifted up and not be damaged with the concrete of the ramp. In these launchings, the normal duration of the operation since the pipes started to be launched till the moment that the pipe is totally installed on the seabed, on the trench, it takes normally 24 hours. This is including the flange connection to the previously installed section. So this is saving a lot of marine equipment time, and that means money at the end. Yes, this is one more picture of the launching day with the 3 railways and the crane helping the flange to go into the water. And as I said before, no concrete collars are necessary. And the other advantage of getting rid of these concrete collars is that in these kind of pipes that they are so big, for example, ID 2.7 or ID 3000, it's not only the cost of the manufacturing of the concrete collars, it's also the cost of the trench that you have to dredge at the bottom of the sea. The cost of that is huge. The marine contractors know how much the price increases every time that you have to increase the dimensions of the trench. So since there are no concrete collars, the trench can be kept smaller. Another project that we have been involved in is in Pagbilao in Philippines. It's a project where a power plant was extending their capacity. So they needed to install an intake pipe of 150 meters more or less. But the singular thing in this case, it was the intake head. The design was not coming from Uponor Infra in this case, but we helped the customer to get the optimal solution. You can see in this picture the pipe while it was being launched, and beside the pipe you can see the intake head body and the intake head screen. That screen there has a diameter of close to 14 meters, 14 meters. This is huge if you have to do it in concrete. Completely difficult to handle, difficult to lift. It's extremely difficult and expensive. On top of that, the customer didn't have the equipment again to handle those heavy loads if it was done with concrete. So we proposed them to separate the intake head in 2 parts. So the lower part was the box that you are seeing there, and the top part is this kind of mushroom you see on the left, and installing them, as I said, in 2 phases and connecting them by bolts. You can see also the same pipe system with the flange connection and the chlorination line with the same system that we used in the other project. This is a closer picture of the intake head that if you look at the first guy on the picture, first guy starting from the left, this guy is 1.95 meters tall. So you can imagine the dimensions of that. This was simplifying a lot all the problems with equipment they had there. If they didn't go for this solution, it would be impossible to install this intake head there because it would be so heavy that no equipment could be used there because they were not available in the country. Once again, you can see how simplified the launching is and how fast it can be. This launching took 45 minutes for this 148 meters long pipe. And here you can see the pipe. Once it has been towed to the sink in place, this is the moment where we were connecting the airbags to proceed to the control sinking. Before this, we have filled the pipe, or after the airbags have been connected, we fill the pipe with water, so the pipe will be submerged, hanging from these yellow balloons. After that, we start with the water filling of the pipe, and after that, we will start to empty the yellow balloons one by one. Once the pipe was installed and backfilled, we continued with the installation of the bottom part of the intake head, this box that took less than 2 hours since it was put in place on top of the sea till it was submerged and connected to the priorly installed string. The same for the top part, with this steel structure, just like a spreader beam. The time that this took from the moment that it was loaded onto the barge, it was approximately 10 hours, including the connection to the bottom part. This is how it looked on the barge, that it's almost full size of the barge. So that's what I said before, that the equipment there was quite limited by capacity and by dimension. So we had to adapt the design for this kind of installation. You can see some pictures of the moment when the top part was submerged. The only thing I can say about this is that the end client was extremely happy, because the time that this took to be installed was reduced dramatically comparing to other options in concrete, and also the price went down considerably for them, because they were reducing a lot of marine equipment. And this is more or less everything I wanted to show you today. And if you have any question, please don't hesitate to contact us, and we will be very happy to answer any question. Thank you very much.
Okay, that brings us to the end of our webinar. I'd like to thank Grant and Pablo for providing us with a great presentation. And lastly, I'd like to thank all of the attendees for joining us today. We will be emailing out PDH certificates this week to all attendees, and we'll also send out this pre-recorded webinar to all registrants and attendees for future reference. If you'd like to watch our previous webinars, there is a link to our YouTube page that you can go on and discover more information from Uponor Infra. So with that being said, I'd like to thank you again, and we hope you have a great day.